Hello everyone, I'm Walter Burgess with Power Technology. Today we thought we'd depart a little bit from talking about cutting-edge laser technology that's available today to talking about laser technology that may be available in 5 years or 10 years. So we're really prognosticating about the future in this video. We find the topic fascinating, we hope you do as well. So today I want to talk real quick about next generation light sources. What's beyond LEDs? So LEDs are so yesterday. LED fixtures have been around for decades. Everybody knows about them. They know they're very efficient. They think about the history of efficiency and they really wonder if there's a next generation light source out there that's going to produce even more efficient light. And we think there is. We think it's laser based. So the common misconception is that all lasers are unsafe. And that's not really true. So people have this common misconception because they've seen James Bond almost die, being cut in half by a laser, or they've seen the fate of Alderaan in the Star Wars franchise be destroyed by lasers. But the reality is that some lasers are safe, and if they're designed properly, there's no safety concerns whatsoever. So let's talk about that era of great advancement. We saw incandescent bulbs come out many decades ago. An average light bulb could use watts of electricity and produce about 60 watts of light. Everybody thought it was great when compact fluorescent lights came out. We were able to gain a lot of efficiency. We moved from 60 watts of electricity consumption down to 14 watts. And that was important because all that wasted energy that was converted to heat was now more efficiently converted into light. And so that was a really great leap forward for energy efficiency. So we learned that lasers can be safe. So let's go and talk about general advancements of lighting technology over the years. So in the beginning we had incandescent bulbs. They produced 60 watts of light, but they also produced a lot of heat and took a lot of electricity. So we introduced compact fluorescent lights and we went from 60 watts down to 14 watts of electrical consumption. This was a great savings. We didn't produce as much heat and we used less electricity to generate the same exact level of brightness. So when LEDs came along, of course, they were a little bit more efficient. So we went from 14 watts of electrical consumption down to 10 watts of electrical consumption. And that was great, that was a good savings. Well, in the future, we think that the future is laser-based illumination, and we hope that we'll provide a little bit more efficiency and go from 10 watts that LEDs use down to 9 watts that a laser illuminated light source can use. So the era of gaining 46 watts of electrical efficiency is over. Now we're really chasing just a few percent of electrical efficiency to make the world a better place. So lasers are going to power the next generation of light sources. They're going to do that by a number of different technologies. So I thought we'd take just a minute to look at those different types of technologies and talk about them. So laser technologies that are replacing traditional bulbs include combining red, green, and blue laser light sources to make a white laser, pumping a phosphor with blue laser light to create white light, or using lasers to put energy into a plasma and generate an ultra bright white light in that method as well. So let's compare real quick LEDs to lasers, and then we'll give you some examples of these different types of laser light sources you may see in the future. So LEDs are great, efficient devices. We really measure their efficiency in electrical to optical conversion, so that's called EO efficiency. Lasers have the benefit of being a little more efficient than LEDs, and therefore that's why we believe they're going to be the next generation of light sources beyond LEDs. There's really no other technology out there on the horizon that's going to be able to compete with the efficiency of a laser. And specifically, we are talking about semiconductor lasers in this context. So the optical performance is also superior with lasers compared to LEDs. That comes from a lot of different properties, but one specific one that's important is the fact that an LED has a large emitter and is considered an extended source by optical engineers. Semiconductor lasers, on the other hand, are point sources, and they have smaller emitters that are less than 100 microns in size. So does this matter too much for general illumination? Well, in some cases it does, some cases it doesn't, but we'll talk about those cases where it really makes a difference here for general illumination in a moment. So one of the examples we wanted to show you was the example of an RGB laser. And in this example, you'll see that we're combining blue light with green light and red light. And when we mix all those colors together, in light-based theory, we end up with white. This is a lot different than when you mix paint. You mix different colors, you get black. So the market economics are really driving the cost of these individual lasers to be lower, and that's why this technology is even viable today, and it wasn't viable even 10 years ago. So another type of laser light source that's on the horizon is the idea of a laser-pumped phosphor light source. So we define this as a phosphor that generates yellow light when it's pumped with a blue light. And by combining the yellow and the blue spectrums, you get a white light output. And in today's state-of-the-art phosphors, you can generate more than 200 lumens for every optical watt of laser light that you pump it with. So let's talk about some examples, some practical real-world way in which these two kinds of light sources are being used today. So red, green, and blue lasers are being used to generate very large projected images in the cinema industry. And in this example, you can see the cabinet on the left holds red, green, and blue lasers, and through a fiber optic, we can deliver that red, green, blue light to each of the different cinema projectors. This is a really great way to generate a very high quality movie image. Another way that RGB lasers can be used is with a new breed of glowing fibers. Now, fiber optics weren't designed initially to lose their light. They were designed to retain their light and keep it in the core. And it's this unique property that allows us to transport data and conversations across oceans. This new generation of glowing fiber is designed to lose its light, and that makes it really effective for architectural lighting, for illuminating inside appliances, or even in automotive applications for trim and just to make the car look a lot more attractive. This is all enabled by the laser's unique property as a point source. So one of the other applications for laser illuminated phosphor, again, is in a cinema projection application. And in this application, we're shining a blue laser onto a yellow phosphor and combining that light to make red, green, and blue or white images on the movie screen. This method has just a little lower quality standard than the RGB illumination, but it's generally used on smaller screens and has an adequate performance. So phosphor can be used for general illumination as well. There's a number of fixtures available that can generate white light using laser as the initial source of illumination, and a phosphor is the way to convert that light into white light. These examples of spotlights are very effective at generating directional light. One of the core components that's used in these illuminaries is shown here. It's a 7 by 7 millimeter component. It contains a laser, the phosphor, and some safety features. And you can use multiple components to generate brighter and brighter light sources. And something in this size scale can be used to generate 500 lumens or 1,000 lumens very effectively. So if you don't need much light, this component may be the best choice for you. So if we want to really think about the future and expand our way of thinking about how lasers could power future lighting operations in a building, there's some work that's being done at Lawrence Berkeley National Lab and other places where they're really considering how could I distribute light throughout a building with a fiber optic. This would be in place of copper as the distributed lighting mechanism. So copper is becoming more expensive, so fiber optics could be a little cheaper. In this illustration, we're looking at a blue light source delivering light to each individual room through a fiber optic. At the end of that fiber, we might have a phosphor, and that could convert the light from blue to white for a specific room. One other exciting way to use lasers in an automotive application is to create next generation laser-based headlights. These laser-based headlights are already on the market in German and other cars, and this really allows us to see beyond today's traditional high beams in today's automobiles. Light-emitting plasmas are being used for research and other applications, but ultimately we're eliminating the need for electrodes, which is the weak link in a plasma-based bulb, and we can inject energy into that bulb using light or radio frequency energy and get rid of those electrodes that cause the bulb to fail fast. So if you want to talk about any future or existing lighting applications that use lasers, give me a call and I'd be happy to talk to you.